Alabama STEM Explorers is made possible by the generous support of HudsonAlpha Institute for Biotechnology, Southern Research, solving the world's hardest problems, the Holly Family Foundation, Alabama Works, Alabama STEM Council, Alabama Mathematics, Science, Technology, and Engineering Coalition for Education, Alabama Math, Science, and Technology Initiative.
Hi, I'm gonna surprise my mom by planting a flower plant for her birthday. That's interesting. Whoa, check it out. The dirt on top looks different from the dirt below the surface. I'm gonna find out why that is.
Hi, I'm Neil, and Nilah and I are here at the HudsonAlpha Institute for Biotechnology. And Nilah was just telling me about the hole that she dug outside.
Yeah, there were different kinds of dirt, all different colors, and they were just below the surface.
Multiple layers?
Yes.
That's cool. So what you saw was evidence of the soil having settled over time.
What does that mean exactly?
So the soil that's in place in our backyard or in the middle of a field is probably not the soil that's been there for millions and millions of years. It's been moved over time, like wind blows dust or floods bring in soil. And then people disturb the ground when they farm or when they build. Animals disturb it. So over time, the soil settles and comes in from one place or another.
So you're telling me that the different kinds of dirt just came in from different places?
Some of them came in from different places, and some of them may have been in response to what else was going on. You know, we can actually build a model that talks a little bit about that.
Okay.
But before we start that, you know that there are 3 layers within the Earth, right? The Earth has 3 different layers.
Yes, the core, mantle, and crust.
That's right, and that was from the inside, the core, the mantle, and the crust. The crust is the outer layer. It's kind of like the skin. The very top of that is where our soil is. So just a tiny, tiny little bit of the crust is actually soil. If you go down you don't have to go down very far before you find hard rock, and that's called bedrock. And that's actually going to be the first part of our activity. So we're going to build a profile of our soil using all different kinds of foods that you might have at home. And there's a lot of chocolate up here.
Yes.
And I am really tempted to just reach out and grab like handfuls of it. So we're going to resist. All right, now the first thing we're going to do is we're going to talk about the first layer, which is called, as I said, bedrock. And that's hard packed down rock that may extend for miles below the surface. We're going to use these candy bars, and if you'll just take those pieces and just layer them here in the bottom. Yep. So you don't find plants down here, and then you can put these pieces in the back. You don't find things like earthworms. This is way down at the bottom. You often sometimes find water embedded in layers of bedrock, and sometimes you even find oil. All right, that's our first layer. Solid rock. Our second layer are your chocolate chips. So chocolate chips are smaller pieces of chocolate bars, sort of, kind of.
Yeah.
And the layer right above bedrock is rock that's weathered. It's broken into pieces. So going ahead and let's pour like half that cup in here. Yeah, there we go. And so these are the pieces of the bedrock. They've broken apart by weathering, either from the movement of water or maybe from the movement of the earth. All right, our next layer is clay. And this is actually, hold out your hand a second. This is crushed peanut butter cookies.
Really? I thought it was graham crackers.
Yep, these are crushed peanut butter cookies, and it kind of sticks together. Clay, when it gets wet, holds together. Clay is great at holding in water, and it's an important part of keeping water in the system. So you can go ahead and brush those in there, and then let's pour in the clay.
Okay.
Now, if you mix clay in with soil and with sand, it doesn't hold water as well as just clay. That's all right. That's all right. Science is messy. Science is messy. No problem. Okay. This layer represents sand. So sand is crushed pieces of rock. You might find really fine sand, like what you see when you go to the beach, you might find bigger pieces of sand. Let's go on ahead and pour maybe like half that cup in there. And at this point now, in our soil, we would begin to see the roots of plants, and we would see maybe earthworms and other insects that live underneath the soil. All right, so there's our sand. Now, not every set of soil is going to have all of these layers. Some of them may have extra layers, some may be missing layers. The soil that you dug in, I think, had all of these different layers based on what you were telling me. Now this piece. These are crushed chocolate sandwich cookies.
Okay.
I have to resist the temptation to just nibble away on these. But go ahead and pour those on to the next layer.
Okay.
And these crushed sandwich cookies represent our topsoil. That's our organic material. That's decayed leaves and plants. This is what's really great for plants. Plants love organic material, the topsoil. And then our last layer, this is oatmeal crisp kind of cereal. You can go ahead and pour that on. That represents dried leaves and maybe dead bugs, and maybe there's some cockroaches in there. And some, yeah, I know. But, okay, so this is the top layer. So there's our profile. And each of these different layers of soil has different nutrients in it, will grow things or not. That's kind of what you saw. Now the challenge is that when you looked at the outside of the dirt, it looked exactly the same across the whole thing. You couldn't look at the dirt and go, oh, look, there's 6 layers under there, right? Geologists can't just look at the surface of the ground and know what's underneath. They can't say, oh, there's water, oh, there's topsoil. So they actually have to do what's called a geological core. So they have to actually drill a hole deep into the earth and then pull out that sample. So we're going to make our own geological cores with these miniature candy bars. Now some of these contain peanuts, some of them contain cookies, some contain caramel. And here's what we're going to do. We're going to actually put this plastic tube on the top and twist and push through, just like that.
Okay.
All right, give that a shot. Let's see what you get. Ah, okay. So,
got some caramel.
Yeah, your candy bar has caramel and chocolate. Mine has just a bunch of like nougat in it. Let's try these last two and see what we get. All right. Ooh, this one's hard.
Yeah, this one's crunchy.
Oh, looks like yours has some cookie.
Yeah.
Mine's got nuts.
Oh.
Yeah. Nuts and chocolate.
Yeah.
So this is the same thing that happens when they do geological cores. They go down in and they pull out, and then they can say, oh, here's this kind of rock. Oh, here's an oil deposit, those sorts of pieces. All kinds of incredible things live just below the surface of the soil.
Yeah.
And it isn't until we core deep into it that you actually can identify things, that you can find out what really lies underneath. So, how deep do you think your plant will go?
I think it'll go to the crushed peanut butter cookies.
I think you're probably right. If you had to dig below that, you would be digging a really, really deep hole. And I don't think your plant needs to go down that far.
Yeah, it doesn't. It doesn't.
And your plant is going to need all of those nutrients that you're going to find in the soil at all those different layers. Fantastic. So, that's what we begin to learn about the soil, about the crust of the earth. And remember, the crust actually kind of floats on the liquid mantle, the liquid surface of that middle layer. And as those plates move and float, that's what actually causes things like earthquakes. But above those, we've got all of these different layers that make up our soil.
Interesting.
Yeah. It is. Who knew we would learn so much with crushed up candy and smashing our way through candy bars? And there we go. There's some background around the Earth's surface.
I've always loved geology. As a little kid, I would pick up rocks and bring them in and clean them with a toothbrush. And you know, science has always been something I loved to do. I always loved those classes in school, and so I came to the University of North Alabama and I took a geology class my freshman year, and I loved it. I'm actually a seismologist, so I study earthquakes, and my degree is in geophysics. So I've kind of combined my love for science and geology, and I kind of do both of those things. So I use physics in my work to image the inside of the earth. What does the earth look like? So it's sort of like a CAT scan or MRI, except you use earthquake waves to image what's happening underground. In a broader context, that's to help with hazards. So why do we have earthquakes? Where do we have them? How big can they be? So math is a big part of geophysics. So math and geology, and we even use chemistry because certain rocks behave a certain way because of what they're made of. So it's a very interdisciplinary area of research. It's so fun. It's one of the few STEM fields where you actually get to be outside. If you enjoy hiking, being out in nature, just a better understanding, gives you much more appreciation for the outdoors. There's lots of jobs. Every little part of geology has a specific study to it. So if you like the mineral part, you can be a mineralogist. If you like rocks, petrology. I'm a geophysicist. You can study about fossils and be a paleontologist. So there's such a spectrum of opportunities within geology as an umbrella.
I'm Kathryn.
And I'm Anderson.
And today we are at Southern Research in Birmingham, Alabama. Anderson was just telling me about a time that he visited California and there was this giant earthquake. Tell him about it.
It was in the middle of the night and it was really scary.
I bet it was scary.
It just felt kind of weird. I don't even know what an earthquake is, but it feels like there's a monster inside the earth shaking everything.
So don't worry, Anderson, there is no giant monster underneath the earth, but an earthquake occurs when there is two fault planes that are slipping past each other. And so if you're ever in an airplane and you look out the window and you can kind of see these giant fault lines. So if you're ever flying over a desert or in the mountains, you can see them a lot clearer. But the earth you can think of the earth sort of like a jigsaw puzzle, and it's made up of 20 different jigsaw pieces, okay? And each of these pieces are constantly moving, they're constantly sliding past each other, but sometimes when those pieces get stuck and they unstick, that would cause an earthquake. And those pieces, in my analogy here, those are called tectonic plates. Are you following so far?
I think so.
So yeah, so slip past. Here, I have a great experiment that can kind of demonstrate that for you. So here we have some delicious cheese spray. Do you like this stuff?
Not really.
Yeah, I don't know who eats that. So what I want you to do is I want you to lay us down a mantle. So the earth is, there are 4 layers of the earth. We have the inner core, the outer core, the mantle, and the crust. And so go ahead and lay down our mantle for us. And the mantle of the earth is pretty hot. And parts of the mantle are constantly moving. There you go. Yeah, that's a good mantle. All right, keep on going. Perfect. Yeah. Okay, that's pretty gooey. This is pretty gross. But it makes for some pretty cool science. All right, great. That is a perfect mantle. Thank you, Anderson. And directly on top of the mantle, we have our crust. So in this experiment, our crust is going to be these 2 graham crackers. So if you want to go ahead and lay our crust on top of the mantle. All right, perfect, just like that. So this is going to represent the mantle and the crust underneath the ocean, all right? And sometimes the crust is going to slide apart, away from each other. So do you want to model that for us?
Okay.
All right, so if it's yep, perfect, just like that. And when this is in the ocean, that mantle is going to come up, it's going to cool down, and it's going to form new crust, all right? But sometimes these plates, if you want to push them back together, yep, perfect. Sometimes they slide past each other. So you can go ahead, yeah, there you go. Sometimes they slide past each other, and when they're sliding, maybe try to slide it in the other way. Yep, they're sliding. And when it gets stuck, a lot of potential energy is starting to build up, right? So there's a lot of potential energy. You're pulling. And then eventually, whenever it unsticks, that is when an earthquake will come. All of those waves from the earthquake, these vibrational waves, are going to come out from the ground, some from the center of the earth, and then some will travel on the surface. But those are the waves that you feel during an earthquake. Does that make sense?
Yeah, it's starting to.
Yeah, and I know you were telling me when you were in California that the TV said the earthquake actually originated pretty far away, right?
Right.
Yeah, and people could feel that earthquake all over, not just in California, but they felt it in Washington and they felt it in different places. And the reason for that is because these vibrational waves will travel in all directions. Does that make sense?
It definitely makes sense.
Okay, cool. All right, good deal. So we are gonna model this next thing with this bowl of water. So we'll put that right here. So to some people, and maybe to our viewers at home, it might be a little confusing how these vibrational waves are traveling in a lot of different directions. But to model this for you, this is what we're gonna do. We're gonna take this pipette just like this. All right, Anderson, I want you to hold this pipette pretty far above the water. I know you got those cheesy fingers, so you're gonna hold it right here on that. Yep, get the bulb in between your fingers right there.
Okay.
Yep, there you go. Now we're both cheesy. All right, now I want you to drop a few drops in there, and you're gonna see the waves. All right, good, perfect. Do you see how these waves are traveling out from the center? Mm-hmm. So where that water is dropping is where the earthquake would originate in this example. But those waves, you're going to be able to feel that earthquake over here and over here. All right, and the way that scientists measure the intensity of earthquakes is by using a seismograph. Have you ever heard of one of those before?
I think so.
All right, well, we have a model seismograph right over there. We're going to go grab it, and we're going to model some earthquakes.
Okay.
Here we have a model seismograph. Now, these are not really the seismographs that scientists use today. Most of the seismograph or the earthquake activity is actually recorded on using computers. But this is a model and it's pretty cool to experiment with. So what I have is a horizontal seismograph. And what that means is that it can only record vibrations coming from a single direction. So for example, this paper, you will pull this paper out like that. Go ahead and you can pull it out. All right, you're pulling. Do you see any lines or any activity?
Yeah, it's just a straight line.
Yeah, it is a straight line. Do you see any squiggles?
No.
Why not?
Because it's not moving.
That's right, there is no earthquake. But now let's simulate an earthquake. So I am going to push this direction. What do you see?
Just little squiggles.
All right, just a little squiggles, and that's right. And so I'm actually pushing from a direction that is parallel to this paper. And this is a horizontal seismograph, so it is recording data from the perpendicular direction. So now what I'm gonna do, keep on pulling, Anderson. I'm gonna push from this way. Now what do you see?
Very big squiggles.
Yeah, very, very, very squiggly. That is right. And so here I'm gonna do it kind of small, all right? And now it's like really, really big.
Whoa.
All right. Yeah, so that would be like a real earthquake or a larger earthquake, the larger the squiggles and the vibrations that you will see.
Wow.
Yeah, and so this can become a problem when there are earthquakes near cities and towns, right?
Right.
So what do you say we build a town and we test out how an earthquake might affect buildings the closer to the epicenter or where the earthquake starts versus the further away? Do you want to do that?
Definitely.
All right, well, here is your hard hat, Anderson, and let's get to work. Oh, man, Anderson, I am so tired. This was a lot of work, but look at this masterpiece we created.
Finally, we're done.
We are the ultimate engineers, and for our viewers at home, the way that we built this Lego city is one, with lots of Legos, but we also have two large pieces of foam poster board separated by bouncy balls and ping pong balls. And the entire earth is secured with rubber bands so that we can easily simulate an earthquake. We can shake it pretty easily. It might not be so easy on our hearts. But are you guys ready? You ready?
I'm ready.
All right, Anderson, we got this. So what we have done is we have our model seismograph right over here. And the earthquake is going to start from this side, and we are going to measure the intensity of our earthquake at 3 different positions. So close to where it begins, a little bit further, and then lastly, even further. And we're also going to see how the distance affects the I don't know, how well the buildings last and if they come crumbling down or not. And it's going to be super sad to see your monkey building fall to the ground.
I know, it's my favorite.
I know it is, Anderson. So, all right, here we go. I want you to start slowly pulling. This is going to be our earthquake data from pretty close. All right, good. All right, look, no destruction. No. Oh, man, there goes our first building. All right, and then we're going to stop it there. Perfect. And now we're going to, first building down. So now we are going to, and that was at 10 centimeters. Now we are going to move our seismograph right here to the middle. And this is going to be 60 centimeters. Are you ready?
I'm ready.
All right, here we go. It is shaking, the earth is shaking, shaking, shaking. All right, good.
Oh man, oh my
Good job. Okay, good job. All right, perfect. All right, and then so we have our reading. We can see that those squiggly lines are getting a little bit smaller, right? They're not quite as intense as they were before, and that is because it is further away from the earthquake. So now we're gonna put it at 110 centimeters away from the origin of the quake. You're gonna pull this pretty slowly, and I'm gonna shake it. All right, here we go. You ready? All right, you're shaking, you're shaking. Oh, there's some cars are falling. All right, good job, good job. So we have some more buildings that are down. But you know, oftentimes, Anderson, it doesn't necessarily depend on the strength of an earthquake. Sometimes an earthquake can be like a medium intensity, but if the earth shakes for long periods of time, that might have more destruction. So are you ready to see what will happen? You can shake with me this time. Are you ready? Let's just give our city a good shake. Go ahead and shake it up. Shake it up. Oh, there it goes. What? No, the whole city is gone. It is okay, Anderson, it is okay. But that's sometimes what happens during an earthquake. But look at our seismogram that we have created. And what you can see, it is a little backwards, but what you can see is when the earthquake, the closer you are to the origin, the more intense the earthquake will be. And as we went further, those lines are less intense because that is the less that you will feel the vibrations. So I'm a little sad our earthquake's done.
It wasn't late until I was in college. I didn't declare a major and wasn't sure what I wanted to do. And then I ended up taking a course called Environmental Geology, which kind of was about the intersection of geology and environmental science and issues like that. Geology is probably one of the most scientifically widespread fields because you have environmental science, chemistry, biology, paleontology, computer science too, and some engineering as well. Here we have geologists that work in surface water, we have geologists that work on the coast in Mobile. We got hard rock guys who work in like Huntsville, Gadsden area. Currently there's a big change towards using mobile devices to collect geological field data. Before you would just have your notebook, you would have a topographic map like the one behind me and you would try to figure out where you are in that map and that would be it. But now you have a super high-powered GPS. You can collect data on your phone, take a picture, it will automatically upload to a map on someone's computer and it's just live geological field mapping, all from someone out in the middle of Alabama back to here in Tuscaloosa. I love my job because I like providing geospatial resources to the public. So we get public requests saying, I want to build on this land, what's the rock type here? Is it going to be safe for me and my family to develop on this property? And we can kind of point them to resources, and we do provide maps and stuff like that to help people feel safe where they're building at. And also just helping the field mappers make meaningful maps that they can then provide to the public.
Thanks for watching Alabama STEM Explorers. If you missed anything or you want to watch something again, you can check out our website at alabamastemexplorers.org. Maybe you have a question we could answer here on the show, and you might grab a cool t-shirt. Feel free to send us a video question or an email on our website, alabamastemexplorers.org. Thanks again for watching. We'll be back next week.
Alabama STEM Explorers is made possible by the generous support of HudsonAlpha Institute for Biotechnology, translating the power of genomics into real-world results. Southern Research, solving the world's hardest problems. The Hawley Family Foundation, established to honor the legacy of Brigadier General Everett Hawley and his parents, Evelyn and Fred Hawley, champions of servant leadership. Alabama Works, a network of interconnected providers connecting business and industry needs to a highly skilled and trained workforce. Alabama STEM Council, dedicated to improving STEM education, career awareness, and workforce development across Alabama. Alabama Mathematics, Science, Technology, and Engineering Coalition for Education, advocating for exceptional STEM education in Alabama. Alabama Math, Science, and Technology Initiative, the Alabama Department of Education's initiative to improve math and science teaching statewide.